Thanks everyone for joining us in our last session of the day and last session of ASFPM. You are in session J3, analyzing and leveraging data for H&H analysis. We've got a great set of speakers today, and I first want to thank Wood for sponsoring this session. So to kick us off, we're going to hear from Seth Lawler. Before I introduce Seth, I'll say who I am too. My name is Mitch Payne, and I'm a floodplain management specialist in FEMA Region 10 out in Seattle. So I'm coming from the West Coast. So our first session today, our first speaker today is Seth Lawler. He's a computational scientist with extensive experience in coastal and riverine surface water modeling. He currently works for Dewberry and has worked on a broad range of projects at the national, state, and local level. And looking forward to hearing his presentation. He's got a co-presenter here today too to help him answer some questions, Will Lehman, and we'll hear from them after their video.
Hi, my name is Will Lehman, and I'm here to present today on Model Library with Seth Lawler and Randy Goss. And we're here representing FEMA and the Army Corps of Engineers to talk about a tool that we've developed, or we're in development of, to help catalog and query flood hazard models in the cloud. So when we think about the federal agencies associated with water resources science, there are many agencies that are working in that space together. We have overlapping authorities, but common missions. And those missions require us to have an understanding of the real-time impact of water resources problems and the planning context of water resources problems. To support those missions, fundamentally, our agencies need to develop models to describe the geophysical reality that we live in and look at alternative analysis or look at the impacts that our regulation might have on flooding in Dallas, Texas today. So all of those things together rely on a background of us having a common understanding of models and model domains across the nation. So some of our agencies might be focused predominantly on weather in the clouds, and others might be concerned more about consequences in the floodplain. But together we make up a group of agencies that have a variety of different models. Sometimes the same kind of modeling frameworks are present in multiple agencies. So if you can imagine, that leads to the development of a lot of different models across these agencies in the same geophysical domain. So FEMA might have all of its regulatory maps that describe the NFIP floodplains stored in the model inventory in the MIP. Whereas the Army Corps of Engineers, for all of its dam safety models, they might all be stored in some other location. And all of these different agencies have their own strategies for storing that data. It might be in the cloud, it might be on a file store somewhere within their agency. The problem is if I, as a user of these models, want to say, has anybody done any work in this location, it becomes really difficult for me to know within my agency or even across multiple agencies whether anything exists in that area. So it becomes really, really difficult to reduce the amount of rework we have when we think about modeling in our federal agency family. So the reality of it is that you kind of have to know who to talk to in order to find a model. So if I were in the Corps, I would need to know who the people that do dam safety models are, and I'd have to go ask them, where do you guys store your models? I would need to know who to ask within FEMA to gain access to the MIP. So you got to know who to ask, and across these agencies, it's rare that we find programmatic access to the data. So you have to have knowledge of the particular modeling application. Like you have to have RAS installed on your computer to understand what the model looks like. You have to understand a lot of pieces of the puzzle that it requires specific knowledge to be able to gather any kind of information. That makes it really difficult. It makes it kind of feel like that we have a library of models out there. It's just a pile of books, kind of as I've described here. What we wanted to do with Model Library was to create some sense of that noise. So the way we did it was we took the notion of a card catalog and the notion of author cards in the card catalog that describe the specifics of the model so that I can get a good picture of what that model looks like, and easily find that without having to know someone special to be able to gain access to that data. So the card catalog really describes what model library is. We're inventorying the list of all of the models that exist out there in the universe in a singular data store that's searchable so that we can find where a model lives in place. Model library is not designed to house all models. It's really designed to store an index of all models so that we can find where things are. Now, not all models are the same. Some models might be consequence models, some might be hydrodynamic models. So we needed to be able to distinguish what kinds of models are out there and what their purposes are. And that's part of the purpose of the model library, is to help identify that. Question becomes, how do we describe a model? So within that, we have an example here of a HEC RAS model. So RAS is a hydraulics model. And on the one hand, we have a geophysical representation of it with the storage areas and cross sections and rivers that make up that model. I can say that's near Roseville, California. But also I have all of the files themselves that make up that model. So the plan files, the geometry files, the flow files, those files constitute what the model is, its purpose is. So being able to query both of those two aspects is important to understand what a model is built for. So we need to be able to describe that. This is just one instance of models that we have to deal with. We also have to deal with mod flow models, or we have to deal with PKFQ models, or HEC HMS models, or Flow2D models, or two-flow models, because our agencies have a variety of models out there. So we tried to create a tool to be able to identify all those different categories of models, and that's done with what we call a model content analysis tool. The model content analysis tool allows us to gather pertinent information from a file store to describe that on the index card so that whenever we search for a model, we can get a good view of what the model is without having the specific software loaded on our computer. Model content analysis tool is a series of API interfaces that has to be implemented, and any model that wants to be included in model library would have to have a model content analysis tool developed. By doing that, we have the ability to then catalog models. So what we do is we connect some sort of file store, that could be an AWS cloud or a network server, to model library, and we crawl through that directory with model content analysis tools. And that's done by the model content analysis engine. The engine then indexes through asking questions of the model content analysis tool to create the author cards inside the catalog to represent the location and inventory of all the models. This is a really useful component of model library, and that piece of the puzzle is developed as a series of RESTful APIs that could be used by a variety of different clients for a variety of different purposes. So that's generally what the model library is in a nutshell. And what I'd like to do now is to kind of hand it over to Randy to show a view of the client that we've developed on the core side to access those models.
Thank you, Will. As Will just mentioned, that the model library is really a collection of very modular components. And so we took those modules and we put them together to create a web client that's serving a number of uses inside of the Corps of Engineers and ultimately for FEMA as well. So the client you're looking at is designed to make it very easy to upload models, to find a model on a map, and also to identify, lists of models via simple searches. So for example, I'm going to look for some dam break models. And so I key in dam, I've got a set of models here represented by cards in this particular view. And I'm going to go ahead and pick a model that was developed for dam break by the Corps of Engineers Modeling, Mapping, and Consequences Production Center. So I'm going to click on Harry Engelbright. So when I go into this model, we have all of the files that were associated with the model, input, output, terrain, everything. They're being stored in Amazon's S3 storage system. In this case, the bucket name is MMC Storage 6. We are not limited to any number of buckets, or for that matter, any number of storage systems. We can work with file systems, Microsoft's Azure, anything we need to work with. So we can just tie it all together. So with respect to the files, we intend to use this is also going to be one of our primary mechanisms to share data with other agencies. So we can go in and select files, for example, and either download and do what we want with them, or we can actually create URLs that allow folks in other agencies and even outside of our agencies to have access to securely have access to very specific pieces of information within our libraries. I can click on metadata, and the MCAT for RAS tools is going to, in real time, read the metadata for this project. So it's going to crawl through basically the project file and extract whatever metadata was entered for the model and display that. It's also going to extract what flow files and geometry files were used for the different plans that were studied. In this case, max high fail, non-fails, a number of different, I think there's about 10 different scenarios for this model. Consequently, I can then go to the map, and very much like the metadata, the geometry information for the model is going to get rendered and reprojected on a map in real time. Part of the capability that we're building out for the Corps of Engineers is to make sure that we can disseminate geospatial data for models and do these for emergency events or whatever events as fast and efficiently as possible. And so the plan is that a model gets uploaded, and at that point, the translations are all part of the MCAT. So the MCAT takes care of the work that we used to have people have to do, because they would have to translate the model format to a GIS format to another format. And so now the MCAT handles all of that workflow and basically makes it automated to the point of where we just expect the model to get loaded in the system, and at that point the data can be disseminated however we need to disseminate it. So at this point, I'm going to go ahead and turn it over to Seth Lawler, who's going to show another application developed with the same modules but serving a somewhat different workflow.
Thanks, Randy. So I want to take just a minute and say, we're talking about this stuff in a kind of a easygoing way, but it's really a system of powerful tools that have been developed. And you know, Randy just showed a really critical application, which is different people in the Corps are working in different offices that need to access or understand the information and modeling tools and models and capabilities that are there. And this is something I think that we all share. Obviously, we've been working on this with FEMA to understand what are the versions of the models that are out there and what's in those models. And if there's a model that is in the inventory, can we use that as the basis to develop a new model? Can we get a head start on upgrading models? There's just a ton of things of utilities that these tools can serve. And so what you saw was a front end, but what's driving it all is a very modular back end that can be plugged in a number of different ways. And so we've developed these. Well, you know, obviously Randy's managing the GitHub channels where we're developing these. But I'll show you another example. Now, this is a slimmed down search engine that we used as part of a project in Texas where we needed to know what models are available amongst other data. So this search engine is going to bring up information about GIS services, web services, information in the system critical for modeling, but also because of the model content analysis tools, we can then inventory those as well. So you can see here on the side, ESTBFE are models that were downloaded from a Region 6 FEMA viewer. MIP are models that we downloaded from the MIP. And so without doing anything extra, we could turn these MCAT tools on and populate databases to catalog, as Will said, the models that we have in our system. And so similar to what Randy showed, we can look, we can search the model inventory, and then we can get information on the specific model. So if we want to know what version this is, if we want to know if there are bridges in the model, or weirs, or how many cross sections, or numbers of streamflow, any number of criteria that we would have that we might be able to want to answer from a model collection, we can do so through these MCAT tools. So for example, profile names, you can see here, there's a 1% annual chance exceeding profile. We might ask the question, how many of the models in the inventory have multiple profiles? How many of them are unsteady? How many have 2D areas? All of these capabilities are now at our fingertips through these model content analysis tools. And one of the other applications that we've been working on through this data collection effort is new data is coming in. And so what the course tool does is does it dynamically. We're using a static approach to inventory models that aren't changing, that aren't serving the same purposes. But it's the same content analysis tools that drive that. So we can make nightly reports as new models come in, are collected and added to the system, and they can be reviewed. And so what you're looking at here on the left is there's a county that we're interested. So we intersect the model rivers that we have in the inventory with that county. And in black, we see the HEC-RAS model rivers that are available. And in blue underneath, the NHD flow lines. So we can do things like understand what our coverage is, where we might need to create new models. And we can answer all of these questions and do many more things with these content analysis tools. So I don't know if Randy or Will, if you guys wanted to have any closing thoughts.
No, I think what I would say is, along the lines of what you were mentioning there, Seth, is what we've tried to do is unlock potential. We haven't tried necessarily to build something that has a specific purpose, but rather we tried to build something that can be used for a variety of different purposes, whether it be inventorying all of the models in the MIP to create status reports, or whether it's to support real-time consequence assessments by getting RAS models to run for emergency missions. So there's all sorts of different tools that can be developed on these stable modular back-end products that we've built. And so, we see the future as being very bright in what we can do with these types of tools.
And all I'm going to add is that we see the future as being very collaborative, that none of these tools are actually proprietary to the Corps of Engineers. The licensing we're using is based on a public domain type license, and we are very willing to collaborate with anybody that wants access to our repos and to be able to, use our products and or contribute to them. So, that's something we've enjoyed about this process, and we've really enjoyed collaborating with the FEMA folks. And I think it's producing a lot of new capability that we wouldn't have been able to do just on our own.
All right.
That's all we have. Thanks a lot for you coming. And we'll be here to answer any questions in the chat.
Thanks, Seth and team, for a great presentation. We have some questions trickling in, but I'm going to start with this one. So they're kind of two combined. Can state and local agencies store or access models on the model library? And similarly, can only federal agencies access the models? Pitch it to whoever wants to answer.
Yeah, I'll take that one on. This is Will Lehman. So currently, the model library instance running off of USACE is accessible by people who have the ability to log into the system. So our login system is dependent upon our CAT cards. So that means that the vast majority of non-federal staff can't access this. So what we've been working on is the ability to access a model library using login.gov, which is a single sign-in source for all, supposed to be a single sign-in source for all federal agencies to authenticate who people are. What that will allow us to do in the long run, we're not through that part of the development yet, will be that anyone would be able to log into this system. Now, the ability to log into model library is different from the authority to see a certain model. So we're very careful about what permissions we put on any model. So that basically means that you might be able to log in, but depending upon who you are and what authorizations you have, you might have a limited set of models. So if someone puts in a publicly accessible model, then you would have access to it. If someone puts in a model that's only accessible to, you know, the double top secret agency, I don't know, then you wouldn't have access. That's so I guess it's a long way of saying our intent is to make this as public as possible, so that anyone can log in, and that models that can be shared publicly will be. So that's, I think that answers the question.
I think so. So another kind of related question is, will all the models used to develop firms and CLOMARs be loaded into this system? And then you may have already answered it, but just want to toss it out there in case, what will be required to access these models?
Yeah, so that's a little bit of a tricky one. So we're developing this infrastructure in conjunction with FEMA as a potential for ways to share models. Currently, FEMA shares models through the MIP. This could offer an opportunity to share models in a new way. We have not agreed upon that at a large scale yet, but if we are able to access the models in the MIP and provide access to that, this could be a way to access the models used to develop firms and CLOMARs. But that's not currently in the development pipeline. We're discussing whether or not that's permissible.
Great. Another question is, can cross-sections data and water surface elevations for specific discharges be extracted from the models in an automated fashion?
So I can take that. Can cross-sections, discharges, and profiles be automated to be extracted? Not currently. It's this is, as we mentioned before, it's a cataloging process. So if you have more advanced needs of the model, then currently those things are not available. This tells you what models you have, where they are, and some metadata. The more features you add, the more close you are to replicating the GUI that the model itself provides. And so these tools they're helping expose models, but not all of the detailed questions that one might ask of a model. It's a good example of a question that if you're looking for that level of detail, you probably want to open the model and see what's going on.
Okay. Another question is, how do you control for model changes and updates?
Sure. So within model library right now, we have the notion of a model having a version, but we do not enforce semantic versioning. So relating back to that question about the models in the MIP, you know, the MIP requires certain models to be regulatory. So our versioning system isn't sufficient to meet their requirements. So we're going to have to work through that detail before that would be a possibility. So right now, it's up to the user to define the version, and there are obvious problems with that and obvious benefits with that. So that's where I'll leave it.
Okay. Another question is, how are the FEMA models getting into the system, and what's the date range of the FEMA models in the system?
Well, currently, in terms of the FEMA models, I think that reference would be more to models in the MIP. We haven't got that. We have no models from the MIP in there at this point in time. So that would be, in terms of the USACE's instance, that would be at a later date that we would get that.
I'll add there that part of the idea was can we investigate using these tools models that are in the MIP? And I think I saw another question about vintage. And so these models do change over time. A version 4 might be different than a version 5. And I think there's a question about geospatial data. So we did download a bunch of data from the MIP to use for testing and development to make sure that when we wrote these tools, we could catch those edge cases and handle those issues. And so the question about what if it's not geospatial? Well, we can tell you everything about the model that's not geospatial. We can tell you what version it is and the profiles and the other metadata that's collected, but we can't put it up on a map.
Okay. And did that answer this next? Support older non-geo-enabled RAS model geometry?
I took a stab at that, yeah.
Okay. Perfect. My non-technical mind doesn't quite connect all the answers to the questions, so thanks. Another one here is related to the hydraulic structure summary. Is there an easy way to access the summary through other applications, or is there a public inventory that can be used to improve hydraulic networks?
Yeah, so I'll take that one on, and really kind of just going back to the core design of what model library is. It's an index to find models and find information about models. So what we created to do that was a set of modular decoupled systems. So there is an API to query if you have authorization. If you have authorization, you can query information about a model through our API. So you can get information like, can you deliver the model to me? Or can you give me a convex hull that describes the entire model? Or can you give me the cross sections, the geometry data? So all of that is possible through the API, but again, the authorization on that API is what limits its access. So it would have to be a question of, it's kind of a two-part question. Is there the capability? And the answer is yes. But that doesn't mean that you now have access to all models that are out there. You would only have access to those that you have permission to.
And I'll jump in there as well. One of the core capabilities that we wanted was this, right? The answer to the question, how many models in the current inventory have hydraulic structure? Or how many have levees? You know, these are components that are critical. And traditionally, you have to open the model and look at it to answer that question. But these tools will allow you to search for that. So I've got 50,000 models on my server. I just want to take a look at those that have hydraulic structures and then see if we need to update or change anything. So that's exactly the kind of use case that we were looking for when we developed this.
Yeah, or the question, how many of those models, hydraulic models, are RAS models? How many of them are RAS 4.0 models versus RAS 5.3 models? All of those questions would be the kinds of questions that we can ask. And what's the geospatial domain of all of our modeling in terms of square footage? You know, all of those questions are accessible through our APIs or interpretation of the data that you get back from the API.
Yep.
Great. And then the last question that I see in here is, what about models at the FEMA library on disk?
So, yeah, I saw that question. So I'm going to interpret that as someone has a local copy. So if you recall back to what Randy said in his presentation, we tried to abstract the notion of a file mount so that if someone had a local file mount, they could actually mount that in the system. The problem is accessibility. Once you mount that as your store, no one else would have access to that store unless they have access to your network. So it's kind of, I wouldn't advise that as a way of storing data, but it can be used for that use case.
I can't help myself. I just want to make one more little plug to put on a cap on what Will said. One of our intents was to be flexible, and so the MCAT can be written in any language. We've written them in Go, we've written them in Python. They could be written in Java. They could be written in any language. They speak HTTP protocols. We also made our search engine flexible. And so, like Will said, you can search a local file store, but you can also search Google Cloud or Azure Cloud or AWS Cloud or any other system. And so we tried to build them with the flexibility to handle all of those cases.
Okay, great. Well, thank you both for a great presentation, and thanks everybody for asking great questions. That's all the questions that I see. So we'll go ahead and move on to the next presentation in this session.
Thank you.
So the next presentation is going to be from Souid. He's a licensed professional engineer with a PhD in environmental engineering from State University of New York. He's been with Wood since 2005, where he's currently serving as a senior water resources engineer, and his area of expertise is coastal flooding, riverine hydrology and hydraulics, watershed studies, risk products, and software tool development. So we'll hear from him and then take questions.
Good afternoon, everyone. This is Souid from Raleigh, North Carolina office. My presentation today on the uncertainty and sensitivity analysis for risk assessments and planning. When we have real-world problems, sometimes we represent the problem with physical model. In other words, a physical model is a constructed copy of an object. An example, wastewater treatment plant, if I need to model and see the variables and the outcome from the plant, I construct a model. Riverine and coastal flooding, another example of physical model. Solar and climate system. Several approaches to conduct physical model. One of them is called deterministic modeling approach, and this is a very common modeling approach that we use all the time. Basically, we have input variable, could be one or more, and we assign value for every variable, and we run the process and to generate the output. The assigned values to the input variables called nominal value, and this is based on best guess. Can be likelihood, best value possible, can be generated from engineering judgment or calibrated data, can be from published reports or some publications. So this is the source of the assigned values that we use for the input models. The assigned values is based on mathematical properties, which is very known. For example, I am using an average value for the input. So nothing is random. When we run the model for the certain assigned value, we always have the same output. No matter how many times we rerun the model, we will have the same output. So there is only one answer to the modeled problem all the time. So planners sometimes they ask another question. They say, what happens if the assigned value is different? So in the first run, we use, for example, the most likelihood value. But what happens if we have a maximum value for a certain input variable? Then you need to rerun the model again. So for every assigned value, you have one output. Sometimes there is another question, which is how sensitive the output to a certain input. Then what we need to do is to run sensitivity analysis, where we select one input, usually at a time, and assign a change or an error to the input. So either plus or minus, we introduce that change, and then we generate the output. So by doing that, we can know the variability of the output impacted from the change that we introduce to the input value. And the change can be, for example, an error in reading, or can be, for example, different assigned value based on engineering judgment. So somebody using the average value of an input, somebody using the maximum one. So this output also is very helpful for the planners and for the engineering design, so they can know the sensitivity of the output here also. So the deterministic model is very helpful, and the sensitivity analysis also very helpful to run for every model. But one thing is the output generated does not have the full range of all possible output from the model. So we don't have worst case scenario, best case scenario. We don't have a probabilistic distribution of the output. What we have only one value or possible couple of values based on the sensitivity only. That's why uncertainty analysis is very important to run in a physical model. The uncertainty analysis is using probabilistic stochastic modeling approach, which is initially done for financial system like Wall Street and all of the financial institutions. This type of modeling produces a forecast of probability of various outcomes under different conditions using random variables. So nowadays, the agencies, modelers in many industries use and employ stochastic modeling approach to improve the engineering and business practice and decisions. In this stochastic approach, if you have an input variable, one or many, each one you need to study the statistics of every input variable. So you have to know what is the minimum value, maximum value, and what is the distribution of the input. This distribution will define the range of every input value. So if you have 10 input variables, you will have 10 different probability distribution functions. Once you have the probabilistic distribution functions, you sample in a random way and independent way a value from every probability distribution function, and then you run the model and you generate the output. Since you are going to do so many rerun, you will have number of output is equal to the number of the rerun. So at the end, we will have a probabilistic distribution of the output. So the uncertainty analysis, in this case, what it does, it studies the combined effects of all of the change or possible values of probabilistic distribution of the input. So this will be a complete combined effect. So we are studying and we can generate the full range of all of the output. And the mathematical model for the uncertainty in analysis can be little bit one step for effort step that we need to do, but it's very important to have a full picture of the risk generated from the model itself. So once we have the full range of that probabilistic distribution, it will help planners and decision makers to understand every possible outcome from the model. So that's the output generated again is a probabilistic distribution function, and we call it in this case a PDF in the presentation. One methodology to do the probabilistic distribution is called Monte Carlo simulation. And the Monte Carlo simulation is a probabilistic method used in modeling natural system, investment, or engineering problems. It's used to simulate the process that is influenced by random factors. The name Monte Carlo comes from the Monte Carlo city in Monaco in Europe. And this is because of the city fame for the casino, which contain large number of roulette wheels, one of the simplest mechanical device for generating random numbers. Monte Carlo simulation use pseudo number, and this is a computer-generated random number and for the sampling technique. The methodology to do the Monte Carlo, you study the problem so well and you study every input variable. Then you have the statistics of every variable and you establish the probability distribution function of the identified variable. Then you do the sampling technique using the random number, pseudo number, so the numbers and the sampling has to be independent and has to be random. You sample from every probability distribution of every input variable. Then you execute the model. Once you execute the model, you get the results. So for every sampling from the input variables, you will get one output. But if you rerun the model many times, at the end, you will have an output distribution. You will have number of outputs equivalent to the number of rerun. So if I run the model 1,000 times, I'm going to have 1,000 output. If I run the model 100,000 of times, I will have the same number for the output. And depends on the complication of the problem, you may run it so many times. For example, in financial institutions, I saw they are running simulations maybe 100,000 of times. I have run Monte Carlo in many case studies and usually like 30,000 times. So this is the framework how to do Monte Carlo simulations. And so the final product is a probabilistic distribution of the output. Obviously, this is a complete framework that can be used in electrical, in engineering, in environment, in coastal, in riverine flooding, in dam breach. It's just a framework to do the analysis. To illustrate an example of the framework, I'm going to use a conceptual rainfall runoff model. And the question here is, what is the peak discharge? Different agencies have different requirements for the peak Q. And so even engineering firms, they have different criteria for the design. So now I am going to study the rainfall runoff model and to generate the probabilistic output of the peak. And for this example, I am going to have several variables for the rainfall, some variable for the runoff catchments, and I'm going to use Monte Carlo simulation in order for me to generate the probabilistic distribution of the output, which is the peak discharge. The rainfall model can use the actual data or can use synthetic storm like SCS storm, or can use mathematical model. In this example, I'm using mathematical model. Every storm has a dynamic movement. The basic element for every storm is a cell, rain cell. And the cell has a correlation in time, which means rainfall falling at any instant is correlated or impacted by what happened at the previous time. There is a correlation in space. Rainfall falling at any point is correlated or affected by what happened at other point within the area of interest. If I look to the rainfall model here, I'm going to use three variables. One of them is how many cells in the area. And then the second one will be the intensity of the rain cell. Every cell has this shape. So what you see is the maximum intensity. So the cell intensity is a function of time and space. The third variable will be the diameter, the extent of every cell. These three variables I'm going to use to model the rainfall component of the rainfall runoff model. So the first variable, I'm going to use Poisson distribution. The second one, I'm using exponential distribution, while the third one is logarithm normal distribution. And this is based on a literature in the meteorology. The runoff model, I'm going to use overland flow and interflow. And interflow, just a reminder, is the quantity of water entering a stream after moving laterally through the shallow soil layers. And then I'm going to use the infiltration process. So the runoff model, the overland process, the uncertain component here is the Manning coefficient or resistance, which is a function of many factors like cover type, soil type, slope. This makes these parameters in the uncertain quantity of the overland flow process. So the question we are trying to solve in the Q, many coefficients here has inverse relationship with the Q. So the more N, I will have the less Q. The interflow, I'm going to use Darcy law, and it's related to, there is a relationship, direct relationship, nonlinear between Q and hydraulic conductivity. The infiltration process, I'm going to use, excuse me, the final infiltration, initial infiltration, and the decay rate. So the first variable, I'm using uniform distribution. The second variable, I'm using logarithm normal distribution, where the third one, I'm going to use logarithm normal distribution as well. So the rainfall and runoff model is going to be stochastic, meaning probabilistic in the rainfall, and also probabilistic in the catchment itself. When I run the model so many times, so I have 3 variables in the rainfall and 3 variables in the catchment, I will end in a probabilistic output. This probabilistic output, every run, I will have 1 value, every run of the model. So I did run the model 10,000 times. This probabilistic distribution will have a minimum value, maximum value, and mean and standard deviation. So from this distribution, I can generate a cumulative curve, and also I can generate exceedance probability curve. So every run here is coming from a combined effects of all of possible value from the probabilistic distributions of the rainfall variables and the catchment variables as well. So if I transfer this probabilistic output into exceedance probability, I will have such a curve. And the way I read this curve, I will say there is, for example, 10% chance that the flow will be about 300 CFS or more. So I will have a 40% chance that the flow will be 180 or exceed 180. So in this case, this will give me a probabilistic sense of all of the output for the worst case scenario and the best case scenario. So if I need to simplify this curve, I can have a table like this. So planners, engineers, everybody can read the data like so easy. So here, for example, I have a 20% chance that the flow rate will be or exceed 216. I have 70% chance that the flow rate will be 65 or exceed 65. So all of the planners can have a probabilistic sense of the flow rate rather than one value only. So that's the exceedance probability curve of every model. Let's look to this model again. What happens if I have a stochastic rainfall, meaning probabilistic distribution in the rainfall alone, while I have a deterministic catchments only? Or what will happen if I have deterministic rainfall and the stochastic runoff only? And at the end, again, I am going to have a probabilistic distribution of every output. So case 1, I'm only varied the rainfall. The catchment is based on nominal value. Case number 2, vice versa, is going to be deterministic rainfall and stochastic model. So case number 1, when the rainfall is probabilistic, I generated 1,000 run, and I have a probabilistic distribution of the output, which is the peak flow. And I have all of the statistics for that variable, and I generate the exceedance probability. Here in this case, there is a 40% chance that the flow rate will be 160 CFS or exceed 160 CFS. If I need to generate the case number 2, I will have a different probabilistic curve. Here in this case, the rainfall is based on nominal values, a sign value deterministic model, while the catchment only is stochastic. I generate also all of the statistics for this curve and the exceedance probability as well. In this case, the 40% chance I will get about maybe 63 CFS or more. So if I need to compare case number 1 with case number 2, I can draw the two curves on the same plot and the same scale. As you see here, the stochastic runoff is very steep curve, while the stochastic rainfall is very mild. This will tell me that based on the selected nominal values, the bulk of the forecast uncertainty is due to the uncertainty in the rainfall model and not in the catchment model. So we need to do more care to estimate the rainfall model parameters than the catchment model parameters, because the bulk of the uncertainty is in the stochastic nature of the rainfall, and that makes sense. Another things we can do is uncertainty importance, which measure the relationship strength and the kind and the rank order of the variables. So I can know how strong the input values to the output and what kind of relationship between the input and the output, and at the same time, ranking all of the variables according to their importance. So the uncertainty importance method can use several statistical methods, and you can use SAS, MATLAB, you can use any software, statistical software. It can measure the correlation coefficient, which compute the relationship between the sample output and the corresponding sample values of every input variable, or can use regression analysis, or can you use rank order correlation, which measure the nonlinear relationship between the input and the output. So the methodology to do the uncertainty importance, that we need to analyze the variables and the outcome. You plot the variables of the input with the output, and you determine the relationship, linear or nonlinear, between the input and the output. And you need to select sensitivity analysis method in order for you to determine the uncertainty importance. This is an example of a scatter plot between Manning and between flow rate, the output. As you see here, Manning coefficients show a nonlinear inverse relationship with the predicted peak discharge. In other words, the higher the predicted peak flow rate, the lower the value of the Manning coefficient. And this is consistent with the inverse mathematical relationship between Manning coefficient and overland flow. The second example is the relationship between the decay rate from the infiltration and the peak flow. It shows clear direct relationship between the infiltration decay and Q. The higher decay rate, the higher the predicted peak, excuse me. And from the infiltration equation, we saw before that for a certain time that the higher decay rate means the lower infiltration rate. So less water infiltrate into the ground. So we have a higher overland flow. So it makes sense that the more decay is the higher Q. Another example here is the relationship between initial infiltration rate and Q, and the relationship is completely unclear. So you don't have either inverse or direct relationship. Another thing to do, as we mentioned, the rank order correlation. When you run that methodology, you can rank all of the variables according to their importance. One of them, for example, Manning coefficient, is more important than initial infiltration rate. So we need to focus more on estimating Manning comparing the initial infiltration, because any change in Manning will make more impact on the output. The sign here, minus or plus, it shows either inverse relationship or direct relationship, plus direct relationship, and minus is inverse relationship. For the rainfall model, the uncertainty is becoming how many cells in the area, and that's more important than the cell diameter. And all of the three variables I selected have a direct relationship. So the summary of the example case, Monte Carlo simulation is used for hydrological model and to plot the exceedance probability. And the case also showed the bulk of the uncertainty is coming from the rainfall model and not from the catchment. The conclusion of this work is reliability analysis is very useful to be and has to be performed to understand the uncertainty in the variables and the outcome. Exceedance probability curve also is very useful
we had about
for
2
the
minutes
planners
left.
and for the engineering design. And I demonstrated how the exceedance probability curve can be done. But uncertainty analysis will give a full understanding of all of the outcome from a physical model. This is the conclusion. If you have any questions now or later, please don't hesitate to email me at my email here. Thank you so much.
Thanks, Al, for a great presentation. It was very interesting. So we'll start out with the first question from the Q&A. Sesh asks, when you do the stochastic modeling, do you remove the deterministic components? For example, seasonality or deterministic trend, or leave as is?
The idea of the presentation and the simulation is to simulate all of the uncertain input variables. So if you are certain from variable, like certain variable, then you can have a deterministic value. As an example, if you go to the field and this value here I collected and it's true, so there is no reason maybe to make any variation to that variable because it's a very certain. So the objective can have two objectives actually. One of them is just to focus on the uncertain variables and run the model. And then another objective is, okay, even you are certain from this variable, but the question becomes, what happens if that variable is shifted to the left or to the right in terms of the value itself? So here, when you do the simulation, you are asking actually what if. So that variable here can have a different value. So really related to what is the objective of the study. So, but the data framework is to consider all of the possible values. But again, if you are confident from a certain variable, then there's no need to change it at all. So you can keep it as is. That's why in the table and in the framework, I mentioned that you need to study well the problem, the physical model, and then start selecting, okay, these are the variables that I have a question about. These are the ones that I am going to use a probabilistic distribution for this input. And then you run the model.
Great, thanks, Al. So another question is, are there ways to calibrate stochastic models with peak flows from USGS stream gauges?
So that's a good question, actually, because with the time limit on the presentation, I did not have the chance to show what kind of information we can derive from all of the data. You have so many data. So you have so many runs for the input. You have so many runs for the output. And so these runs is not just giving me a probabilistic sense of the target, like for example, in this example, a peak flow, which can be used for, again, like all of the probabilistic can be used like for, we have been seeing a graduated flood risk. So now we can know every possible chance according to the target, which is a big flow. In terms of calibration, this data can be used so well for the calibration. So people usually in general, when they calibrate, they change, for example, certain value, let's say Manning, and then they look to the stage or they look to the volume. Here we have so many input with the output. So when you construct your model, let's say you have 3 inputs. You are varying the variability here. So every run, you can construct your model that every run will have a row similar to the attribute table of ID. So you have this run, you have 1 input, 2 input, 3 input, and you generated 1 output. But if you have, let's say, 10,000 runs, you will have 10,000 output. When you rank all of these target and the output, then let's say, for example, you want to match and calibrate your HEC-RAS model. So you match the output value that you need to calibrate with the row with the input value. So if the target, for example, is stage, you know that I need to have, let's say, a stage 20 feet. So the target in this case in your problem will be the stage. So you look to the stage, which is like we said in that example, for example, 20. That 20, what is the corresponding factors of the input? Input 1, input 2, input 3. So you can, with the data you have from the input and the output, you can derive so many output generated, not just a probabilistic sense or relationship or ranking relationship, but also you can know at which value of the target or the output I need to have my input. And obviously, when you construct your model, the input has to have a certain range. So you are saying, okay, I am going to vary this variable, maybe this percent, like 3-4%, but this variable here, this variable here. But the combined effect will generate a 1 target, and that can make the calibration is so easy.
Okay, great. Well, thank you so much, Al. Thanks for answering these questions, and thanks for a great presentation.
Okay, thank you.
So next up is Peter McCarthy. He's the USGS StreamStats coordinator, and he's got a live presentation. So I'm going to let him add any more introduction that he wants. Take it away, Peter.
Thank you, Mitch. My name is Peter McCarthy, and I'm the USGS StreamStats coordinator, and I'm presenting, I guess, live today from Helena, Montana, or just outside of Helena. I've been with the StreamStats team now for almost 4 years, and I think I'm still learning about everything that StreamStats does and still looking towards new functionality, new capability that I would like to bring into StreamStats, like stochastic models like Al just presented on. I remember about 3 years ago in Phoenix when I and Andrea Veilleux did a workshop on Bolton 17C methods. We were the last session on the last day, and I felt like the audience was rather weary. So today I don't actually have to get that feeling from the audience as I present again on the last session on the last day. So hopefully you can stick with me and we'll get through this presentation. For many of you who've gone to multiple conferences, the StreamStats presentation is one I frequently do at ASFPM. And so really this is just an update on what's new, what's coming in StreamStats. And hopefully for those of you that use StreamStats a lot, this will give you an eye into things that we're currently working on. So today's topics, again, is, what is StreamStats? Who uses it? Some very basic slides. Many of you have probably seen these before. How is StreamStats developed, or how do I get it developed in my state or region? We're going to talk a little bit about the StreamStats ecosystem of services. We no longer really refer to StreamStats as a single thing, but more as an ecosystem of modular services and APIs or clients to access data and services. I'm briefly going to touch on selected user stories, and then we'll jump into a summary. So what is StreamStats? I like to refer to StreamStats as the bridge between USGS reports and users who need to access information, capabilities, or tools that are referenced within those reports. Traditionally speaking, we're talking about streamflow statistics and methods for estimating streamflow statistics at ungaged locations. Traditionally, USGS hydrologists and authors will go through and analyze streamflow statistics at USGS gauging stations, and they will publish those statistics. They may or may not also develop methods for regionalization or estimating streamflow statistics at ungaged locations. These methods and these statistics come into StreamStats. We develop the tools to delineate the basins, compute basin characteristics, retrieve published streamflow statistics, or solve regression equations for estimating those values at ungaged locations. That's the core functionality of StreamStats. That's, what StreamStats was essentially developed to do. So it's for users to come in and get streamflow statistics at gauged locations and ungaged locations. Over the years, and that's almost 20 years of StreamStats being a USGS product, we've added a number of other functions and applications, and we're broadening our capabilities within the StreamStats realm. And that's really why we call it an ecosystem now. Again, this is a common slide I present, is who developed StreamStats. The data, the applications, the availability of the equations, the at-site statistics, those are all done locally by the USGS water science centers and authors or hydrologists within those water science centers. And so every state is a little bit different on what statistics are available, what geospatial data is used, what underlying geospatial digital elevation maps or watershed boundary data sets are used, whether they're using an NHD plus product or they're using a LiDAR derived product. Every state is a little bit different, and it's optimally created based upon the funding and stakeholder interest. When we talk about StreamStats, the driver has always been flood frequency equations for floodplain design, for infrastructure design, for estimating those values at gauged and ungaged locations. Taking a look at our map here, we recently brought Puerto Rico into the StreamStats realm. We now have delineation and basin characteristics capable Puerto Rico version of StreamStats. The Caribbean Water Science Center is continuing to work on peak flow regression equations for Puerto Rico as well. You'll see a number of blue states on this map. Nevada, Wyoming, Nebraska, Louisiana, and West Virginia all have applications of StreamStats undergoing implementation. We expect to see West Virginia to come into our StreamStats realm yet this fiscal year. We're going to get a pilot basin from Wyoming this year. Nevada, Nebraska are definitely down the road 1 or 2 years. And Louisiana is probably going to be early next fiscal year. A new figure I haven't shown before is the application by resolution. As I indicated earlier, there's many different resolutions or underlying data sets in StreamStats. Some can be based on NHD plus data sets. Some are based on medium res NHD plus. Some are based on NHD and 10-meter digital elevation maps, and yet others are based upon LiDAR. So as you'll see in this figure, we've got Nebraska coming up that's going to be based upon a 3-meter LiDAR product statewide for Nebraska. In other states, we're actually refreshing the underlying data sets. In Pennsylvania and in Delaware and in Indiana, we're refreshing the underlying data sets to improve the basin delineation capabilities to make those more accurate. Who's using StreamStats? We have 321,000 sessions in the last year. As expected, most of those are coming from the United States. But what's really interesting is that we have a large number of users in states that don't yet have StreamStats. And I liken that to the fact that those are likely contractors doing work in other states. For many of you who are familiar with StreamStats, you probably use our web interface. And that's where I was talking about 321 sessions initiating our web interface. The web interface is really built around a single click point. A user knows where they're working, they know where they want to get a value, they go in and click that point. But we also have a batch processor where you say, I need values for 100 different points give me a shapefile, put it into our batch processor, we'll crank on it, and in a day, we will give you a place or location where you can go download those results from the batch processor. And then the third piece here that's not used widely yet, but we are seeing some implementation is our services. We have broken apart StreamStats as a one all-encompassing program into a front end and a back end that has services. And so we have different services for basin delineation, for computing basin characteristics, for solving regression equations. And those services can be programmed into your local application or into your local function where you're wanting to hit those asynchronously. If you're a user of StreamStats, you might notice that we have a little tell us about how you use StreamStats link down here at the bottom of our, or on the left-hand pane of our application. Please, if you are a user, please go in and fill out the survey. It's really important to us to know how StreamStats is being used, and it's going to be really important as the water mission area, the USGS, looks into the future of how do we support StreamStats and what can we do to improve upon the at-site statistics delivery and methods to estimate values at ungaged locations. So improving the data and the tools, this is when I start getting into one of my more favorite conversations. Really this is about how do we do a better job of what is in StreamStats. And the number one thing that we can do is really go to LiDAR-derived products. LiDAR-derived products really help us in these flatter areas, but they can also really help in improving really where those ridge lines are that we traditionally use the watershed boundary data set. But we also need to start revising what I call structure or stream locations. Where is that culvert and where should that stream cross the road? I really would like to see a culverts database that's a CONUS wide capable. And that's why I was asking questions on the MCAT model earlier about, wow, are those cross sections or is that structured database available for us to jump in and get at? And then we're developing or redeveloping tools. Our data processing tools have been redeveloped. We're creating tools to better selectively enforce drainage locations across roads. We're talking about pre-solved basin and streamflow characteristics. We now have the ability to delineate through pipes and storm drains, and we've implemented that in St. Louis, and we're working on that outside of Boston in the Mystic River Basin. We also work with water science centers to improve the science. And really this is about improving at-site statistics, the explanatory variables or basin characteristics that are used for regression equations. How do we go beyond multiple linear regression equations and go to machine learning? What other tools can we provide? Can we implement stochastic modeling? Essentially, StreamStats is really about being adaptable to our stakeholder needs through the water science centers. So again, improving the science. We see a really high focus on users in StreamStats on small basins. We recently did a query of our Google Analytics and StreamStats, and we found that over 50% of basin delineations during the month of April were done on basins smaller than 2.5 square miles. And so this really tells us as USGS that moving to LiDAR data and moving to the ability to better delineate small basins is really important to our users and our stakeholders. The ecosystem of services. Really, this isn't just StreamStats anymore. It's a full ecosystem. It's services, it's functionality that's within the application that is also service-based. There's a large list here. I'm not going to go through the entire list. Some of these things we have in StreamStats, some of these things we're currently developing. Some of these in this list I'm going to talk about in the next few slides. So as you know, StreamStats does a delineation. And this delineation is really paramount to building trust from the users about the data and the resulting estimates. If the basin delineation looks wrong, we lose trust. The beautiful thing about StreamStats is that we have the ability to let users edit that basin delineation if they see an error, and then compute new basin characteristics on the fly that go into that regression equation. So here's a case in a place in Montana where we have a basin delineation that is incorrect based upon the underlying NHD plus version 2 data sets that were used. At-site statistics and data, again, we have published data with citations that are implemented into our database. We also have published basin characteristics. When we jump into streamflow statistics, you'll see that we have unregulated, regulated, weighted with regressions, regressions only, maybe based on record extension methods like the move3, or in some cases we have an alternative for all other cases where maybe there's some additional analysis that went into that characteristic or that value. So when you are using our statistics, make sure that you understand what statistics are available and which ones you're using. Is weighted the most preferred value at this particular location? Or is this a regulated gauge that you really should be using the regulated streamflow statistics analysis? At ungaged estimates, we have the ability to go in, delineate the basin, retrieve those variables or values and plug those into regression equations. Again, depending on which state you are in or which application of StreamStats, you may have only peak flow statistics, or you may have a whole list here of different stream flow variables that you can solve for. In addition to just solving regional regression equations, we have other methods for finding stream flow values, whether that's pre-solved values from the Permanence of Flow or PROSPER project, a flow duration curve transfer method using near real-time estimates to recreate hydrographs, or maybe it's weighting upstream or downstream with a nearby gauge, doing a drainage area adjustment. There are multiple methods within StreamStats to actually go in and improve your estimates. We have the ability in both Colorado and Montana to look upstream and find reservoirs and the percent of the basin that is regulated based upon those reservoirs and the drainage to those reservoirs. We're working on a new dam disturbance regulation indice that actually has been published using the NHD Plus version 2 data sets. In Colorado, we have both the TR55 and rationale methods implemented. We are working with the South Carolina DOT to improve upon that and apply a new South Carolina method, which will improve the method for time of concentration, and I believe will also calibrate the peak flows from those methods to USGS regression equations. We have state-specific layers. In many states, you'll see a bridge layer. In some states, we have a dams layer. I'd like to expand that. I'd like to have diversions and culverts. In StreamStats, we have the ability to go upstream or downstream to navigate the network, to look downstream from a specific point and say, how many gauges are downstream? What's the nearest gauge? Oh, that gauge doesn't have a very good record. What's a gauge downstream that has more than 50 years of record? And you can begin to navigate the network and look for gauges with large periods of record. Then you can weight your analysis or transfer the statistics from that gauge to your location, assuming that those methods are applicable. And actually there's a USGS researcher, Ken Ang, who's working on new methods for doing that weighting. So that process that I just described is actually the similar nearest gauge statistics, where you look upstream or downstream, or possibly you can look within a radius and say, I've got an adjacent basin with basin characteristics and streamflow characteristics. I don't have anything close by upstream or downstream. I realize that I shouldn't transfer from one basin to the next, but in some cases there's very limited information or other streamflow statistics nearby. I touched briefly on the flow duration curve transfer method. Essentially, you need regression equations for the flow duration curve points. You need a method for finding an index gauge. Maybe that's going upstream or downstream on the same stream. Maybe it's using some type of kriging method. But essentially, you use that real-time gauge, you use those flow duration curve regression equations, and you can recreate a hydrograph at your ungaged location. StreamStats is an outside application that does apply QPPQ in Iowa, as well as Flow Anywhere in the PRMS modeling results. We're trying to bring all the functionality from StreamStats actually into StreamStats, and the QPPQ, or the flow duration curve transfer method, was the first of those. I talked briefly about storm drains. This is really exciting for me. In St. Louis, we have the ability to delineate a basin, and that basin can be delineated based upon the storm drain infrastructure. Well, in any urban or highly urban areas, this becomes more and more important as we begin to realize that how impacted our peak flows and our true contributing areas are to those storm-driven systems. And so now you can start delineating basins based upon what directly flows to your point, overland flow, or what flows off a street into a storm drain and comes out maybe into your channel or your location of interest that comes as contributions through storm drains. I'm hoping that this will change how the USGS looks at regionalization methods or peak flow methods at ungaged locations. We also have water use applications within StreamStats. The USGS has really been expanding its water use capability. At one point, I was expecting the water use to stand up its own portal. Right now, that actually looks like that may not be happening. So we may continue to build out water use functionality within StreamStats. Ohio water use actually has temporary water use permits where those are submitted from the state agency through USGS and into our system. Currently, this is not live in our application because we are in the process of rebuilding it. And then time and travel is another really exciting application we're working on. It's another front end. It's not going to be built within the traditional StreamStats front end, but this application allows users to essentially plan for and or respond to a spill in a river where you have an injection point or a spill point and you want to know how long it takes for that constituent to travel downstream. We're also building a fire hydrology application to look at peak flows after fire events. Again, we talked about LiDAR. I feel like I'm talking about LiDAR all the time these days, but we're building tools to process LiDAR data to implement that as the base layers of StreamStats. And then an idea that we've been talking about really that's come about is coordination with the National Geospatial Program is scenario-based connectivity. So when I talk about scenario-based connectivity, I'm talking about during a flood event, a big flood event, all these prairie potholes might be contributing to downstream flow, but maybe in a summer in a drought during low flow conditions, they would not. And that changes the delineation of your basin based upon the scenario that you're wanting to work in. And so through using the NHD plus sinks and through using maximum connectivity of a network, you can begin to look at scenario-based connectivity or scenario-based hydrologic networks. Jumping into a few user stories, South Carolina is a great user story. They continue to build out applications and functionality within StreamStats. They were awarded the 2019-16 High Value Research Project by AASHTO. They estimated that they saved $20.3 million over a 10-year period. Pennsylvania is our largest user of StreamStats. They really require contractors to use StreamStats for regulatory permits. They've done a lot of work on low flow, peak flow, base flow, and bank flow characteristics. In Montana, we've built a great relationship with the state DNRC, where we are doing flood frequency basin by basin and getting those analysis, those peak flow analysis into StreamStats. We're really looking more thoroughly at regulated, unregulated, and record extension methods, and really trying to do analysis on all gauges, not just gauges that are used for regional regression. We've always had a really strong relationship with the Colorado Department of Transportation. We're currently looking to a proposal that uses LiDAR data and culvert locations that have been surveyed to improve the hydrologic network used in Colorado. In Indiana, I've talked a lot over the years about the coordinated discharge statistics. It's a memorandum of understanding between multiple agencies that flood frequency analyses are reviewed by the various agencies and approved. And those approved values become the value of record that's used by all agencies until one agency decides to update those. In Indiana, we're also working on a 3-meter LiDAR product in StreamStats, which will greatly improve those basin delineations and characteristics. In Minnesota, we're looking at sediment transport data. We have a proposal to add a service of a calibrated machine learning model to estimate what the sediment transport would be from day to day. And then combining that with QPPQ methods, get recent loads or fluxes of sediment to say reservoirs or lakes, anywhere downstream where you need those estimates. So there, I got through. I think I was on time. Mitch, back to you.
Great, thanks so much, Peter. As someone who works in a region with lots of Zone A areas and a lot of communities that have to deal with this, definitely appreciate all your work. So your first message in the Q&A is a message of solidarity from Steve Story, who says, we're still here for the very last slot of the day. So good on you for sticking around. The first question is, what is the range of accuracies for ungaged basins in Washington State for the Q100 flow?
Oh, that's a really good question. Off the top of my head, I do not know the range of accuracies. I would go to Mark Maston's report to get a better understanding of how the regional regression equations in the regions were developed in Washington, and start looking at the model output standard errors of those models and see how well they do in different regions. I reviewed Mark's report, so I should probably know this offhand, but I'm sorry I don't.
That's okay. Hopefully Jerry can go spend some time looking for that. And Nicole asks, where can I go to find out information on which of the tools are available in my area?
That's a really good question. Many of these tools are state-based, and we don't do as good of a job as we should communicating to the public what tools are available. At this point, if you're wanting to know, send me an email, pmccarth@usgs.gov. I'm more than happy to respond to emails. I do get behind from time to time, I'm sure we all do, but I will respond. I will make a point of responding to emails, especially about functionality and capability. If you're interested in building more functionality, reach out to your local water science center. We try to have all of the collaboration with stakeholders and users go through the water science center so that they can really work with the local folks to figure out what data, what statistics, what methods work best and are needed in that local region.
Great. Well, that is all the questions that we have. So thank you again, and thanks to Al and Seth and Will for their earlier presentations. And thanks all for sticking around to the very end of ASFPM. We'll see you next year in Orlando.